All right. Good afternoon, everybody, and thank you for joining us today. Welcome to the Future of UVEB Advanced Manufacturing Trends, Strategies, and Applications, a regular webinar series presented by the State University of New York College of Environmental Science and Forestry in collaboration with RadTech International North America, the Association for UV and EV Technology. I also want to acknowledge that today's webinar is also being sponsored in part by Nagase America. My name is Brandon Murphy, and I'll be your host today from SUNY ESF. As a reminder, all the webinars in the RadTech series are recorded and archived, and that archive is posted at the web address there, but you'll also get a reminder with that web address in an email after the webinar is over, so you don't need to write it down fast or anything. One other quick reminder, the RadTech 2020 UV and EV Technology Conference is coming right up. It's going to be March 9th through 11th at Disney in Orlando. You can visit radtech2020.com or the RadTech website, www.radtech.org for more information and to register. And I'm pretty sure if you have questions after this, our presenter is going to be down there. You can follow up with him in person if you want. So just some quick logistics before we get started. When the presentation is over, we'll open up a window where you can type in your questions at the end of this, but we're going to hold questions till the presentation is done. Today's webinar is on the introduction of UV cationic curing. It's being presented by Mike Idacavage of Radical Curing LLC with some support from Nagase America. Dr. Mike J. Idacavage received his Bachelor's of Science from Drexel University in 1975 and his PhD from Syracuse University in 1979. Mike's work in the area of radiation curing started at Eastman Chemicals with the establishment of a photopolymer lab in 1985. Mike has continued to work in the energy curable area since that time. In 2003, Mike received the President's Award for Outstanding Achievements to the Radiation Curing Industry from RadTech North America. And he also served as the president of RadTech from the 2009-2010 term. Currently, Mike is an advisor and consultant to RadTech in several companies in the UV and EV curable market, in addition to being an adjunct professor, associate professor here at SUNY ESF, teaching courses in UV and EV curing technology. And with that, I'd like to welcome and thank Mike Idacavage for today's webinar.
Thanks, Brandon, for the really good introduction. And hello, everybody. As Brendan mentioned, my name is Mike Idacavage, and the topic of today's webinar is the basics of cationic curing. Cationic curing, at least UV curable cationic curing, has been around since the early days of the UV curing industry. However, many of us really kind of view cationic curing with as a bit of a mystery, and a lot of unknowns on how you may want to use it and where you can use it. And hopefully in today's webinar, over the next hour, we'll answer those questions. As a start, I'd like to go over the agenda for the webinar. And there we go. I'm going to give a brief introduction to UV curing, and it's going to be very brief, kind of assuming that most of us on this call know some of the basics there. I'm going to discuss the mechanism of cationic curing, and then spend the majority of the time of the webinar going into details on the materials that we use. These are epoxies, epoxides, polyols, additives, and photoinitiators. Various formulating strategies to be able to achieve different properties in your final coating or ink. I want to talk about hybrid systems because they've become a very important tool in your toolbox. And if we have enough time, I'm going to give some examples of some cationic formulations as starting points, or just to illustrate how either simple or complex they can be. Let's going on to the next slide. UV curable cationic technology is used today in coatings, inks, and adhesives. It actually cuts across a wide breadth of applications. But it all comes down to some very simple basics. And I'll start here get everybody on the same page here on what is UV and EV curing. And it's using primarily UV energy or visible light or low energy as opposed to thermal, evaporative, or oxidative air dry type curing. And when we talk about UV curing, we're really looking at somewhere between 200 and 400 nanometer in wavelength. And comparing UV curing process with conventional cure, and on the top there you see the conventional curing process. There we go, where you have your wet application and you have a certain thickness. You have your drying stage, and here, to be a thermal oven, you remove your solvent, it coalesces, dries in seconds or minutes, and then you go down to your dry film with reduced thickness. In UV curing, you have your wet application, very similar to conventional cure. It's then exposed with UV or EB light. You get pretty much instantaneous cure in milliseconds for free radical now. And you end up with your dry film just about retaining the same thickness. You get immediate property development, a very good cross-linking density, and you tend to retain the shape. Now for cationic curing, it works the same way as free radical cure. However, instead of instantaneous cure, and I'll be talking about this shortly, you may have cure stretching out over minutes or hours. You get your initial properties, which will help you do what you need to do, but you'll see an improvement in properties over time, known as dark cure. Okay, let's compare free radical, because most people are familiar with free radical chemistry, with cationic cure chemistry. In free radical, you get the polymerization through double bonds, and it is usually acrylate or methacrylate double bonds that is the most common functionality. For cationic cure, you tend to get more commonly polymerization through epoxy groups. And in cationic cure, cycloaliphatic epoxies are most commonly used. In free radical cure, you use a photoinitiator. It absorbs UV light and it generates your free radicals. So that's how you generate and kick off your polymerization reaction. The free radicals react with double bonds, causing chain reaction, and you get your polymerization and your final ink or coating. In cationic cure, it's pretty much the same process. Here you use a photoinitiator, it absorbs the UV light, and it generates, instead of a free radical, a Lewis acid. It's this acid that reacts typically with epoxy groups, resulting in the polymerization. So instead of generating a free radical, think of it as a very similar process. You're now generating an acid. So to illustrate this, we're going to talk about the mechanism of cationic curing. Okay. And on this slide, you see here the initiation. So the very first step, so we have your photoinitiator is exposed to the UV energy, forms the cation and anion, reacts with a suitable epoxy is the example here, complexes with that, and we're missing a few, it looks like a bond here or so, but basically it reacts and you start your polymerization. Polymerization, so we now have our, there's the arrow here, so we have our reactive species here. It reacts with another epoxide and so forth and so on to get your polymer. At this point in time, it is not reacting because UV light is exposed to it. Once that cation initiates reaction, it continues. Very similar to a classic epoxide polymerization used in thermal curing. So right now we've converted from a UV curing process to really a thermal curing process in your coating or ink. And this is referred to very commonly as dark cure. And I want to comment on that because this can be used very to your advantage when using cationic cure. So when the UV light stops, the polymerization reaction continues. This is commonly called dark cure, and it should be noted it takes place in the presence of visible light or lack of visible light. So it's just a thermal process at this point. So it just keeps continuing. You'll also hear the term post-cure used to refer to dark cure. It's the same thing. And it's basically that continuation of that polymerization. This can be accelerated by heating after exposure to UV light, similar to a thermal epoxide reaction. Okay, and we're missing some of the bonds here I see on this. This should be a polymer connected. But you can also have, in this process, a chain transfer reaction when you have a hydroxy functional material. So in this case, and consider it should be a straight bond here, it reacts with an alcohol, and that will tend to terminate this polymer chain and transfer over to another polymer chain. So you get classic, in polymerization, a classic chain transfer reaction. And this is where you can build up shorter chain polymers. And finally, you'll terminate your reaction because it is possible that the polymer chain here will react with, for example, the anion, cap it off your polymer, and terminate the chain. And on the next slide, I just have an overall view of the process. We won't go through this. It's just I wanted to illustrate this just on one slide, using slightly different monomers and initiators, but this gives you a chance to see how the cationic process works. Now I'd like to move into the actual materials used for UV curable cationic systems. And in this case, we have a formulation, and it's composed of multiple components. Just like in free radical systems or applications, it's not one material that gives you the properties that you want or need. It's the blending of multiple materials together into a formulation, and then using that exposure to UV light to get your cured properties. And a typical UV curable cationic formulation would look like this. You have cycloaliphatic epoxides. These are the base coating properties. So these give you the bulk of your properties there. You'll have polyols frequently. They will contribute to cross-linking and flexibility. You can use epoxy or vinyl ether monomers, primarily for viscosity reduction, but it could increase the rate, as I will show a little bit later. You have additives. They tend to fine-tune your performance, for example, pigments to give color. And finally, the photoinitiator package. This generates your cation, and these are commonly sulfonium salts. So you combine these, expose them to UV light, and you get your final cured product. Something that's a little bit different in cationic cure than it is in free radical cure is that if you can cure these systems by electron beam, so EB curing. However, a big difference, and this tends to sometimes surprise people, is that while a typical formulation may look the same through the cycloaliphatic epoxides, polyols, additives, etc., to cure cationic systems by EB, you need a photoinitiator package because you can't generate cations using the electron beam. So you have an initiator that will break apart. These are commonly iodonium salts, and you'll then generate your cation, and you get cationic cure through exposure to EB, and you get your cured product. Now, this is a pretty rare application of cationic curing. In my career, and it started way back, as Brandon mentioned earlier, in the 80s, I've only been involved in one application of electron beam cationic curing. It's great if that's what you need, but usually due to cost requirements, almost all cationic curing is done by UV light. It works very well, so you really don't need to get involved in electron beam. But it's out there, so I wanted to make you aware of it. Okay, let's start out with the base material. And these are epoxides. Cycloaliphatic epoxides are the most common systems that are used. They're the major component of cationic cure formulations. They're also the major contributor to the properties of the cured photopolymer. You can think of these, for those of you who are familiar with free radical cure, you can think of these as equivalent to the oligomers that are used in free radical systems. On this slide, I have listed what I consider the real workhorse epoxide of UV curable cationic systems, and that's this cycloaliphatic epoxy compound with 2 cyclohexyl groups. I will abbreviate it in the rest of this webinar as CAE. That's just to make it a little bit easier than spelling it out, and it could fit on charts a little bit easier. However, in the industry, there's no really, I think, common acronym for this material. The different suppliers call it by usually different trade names. So anyway, today we'll refer to it as CAE. It's a relatively low viscosity material, 250 millipascals at 25 degrees centigrade, low color, low odor, very easy to obtain this in high purity. And some of the characteristics which really lend itself for it being the workhorse epoxide is that it's highly reactive. You get no oxygen inhibition, which is similar to other cycloaliphatic epoxides. There's very low shrinkage on curing. You get excellent adhesion to metals and plastics. It tends to cure in a high gloss and has very good electrical properties. Now, while this is the major material that's used out for UV curable cationic curing, it's not the only one. On this slide, I illustrate some of the others that you can use, and we are again missing some double bonds here. So when we post this webinar online, we'll make sure we have the right structures there. They have this material, cycloaliphatic epoxide, for increased flexibility. There's another one for flexibility. This should be a double bond. We lost the vertical bonds here. And then we also have a DuCure, which is a cycloaliphatic epoxide and a methacrylate. Okay, we can also use non-cycloaliphatic epoxides and to modify your properties in your materials. For increased toughness, we have this bisphenol A type system here, aliphatic epoxide. We have an epoxy Novolac material here. We can increase toughness, and very difficult to see, but it's another phenol-containing group, and then a long aliphatic chain, and we're missing connecting bonds here, for increased flexibility. Now, why are cycloaliphatic epoxide materials used over the, say, the regular aliphatic materials? Here's some work that's been reported comparing CAE with glycidyl epoxide. And this is an aliphatic chain with just an aliphatic epoxide here. And you can see here on the x-axis here in time, when combined, you get the CAE kicks off first. So you get that reacting quite rapidly after about 50 seconds. Yet it's a little bit over 100 seconds before we get the glycidyl material starting to react. On this chart, we could see perhaps a more interesting or a little bit different example of the epoxide structure and its effect on reactivity. So we have, this is work done by Alec Scranton, University of Iowa, and we see here he compared cycloaliphatic epoxide with this glycidyl, and then with this just a simple aliphatic system. And you can see how rapidly the cycloaliphatic epoxide will react with the cation, and you get conversion much quicker than either the glycidyl or the aliphatic system. So this illustrates very clearly why cycloaliphatic epoxides are the workhorse in UV curable cationic systems. There's another cyclic material that is used, and in fact it's being used more and more for a lot of good reasons, and that's using oxetane structures or oxetane materials and using them in your formulation. This is the general structure of an oxetane here, and I'll have some examples of commercial material in the following slide. But oxetanes tend to give a very good combination of both hardness and flexibility, so good balance there. You get excellent adhesion, solvent resistance, abrasion resistance, and you'll also get less shrinkage than cycloaliphatic epoxides. So they're a very good material. They tend to probably cost just a little bit more, so they're used in balance with cycloaliphatic epoxides most commonly, or in combination. So here's some examples of oxetane structures. I have the initials there. They're known as EHO, OX, MA, etc. But you get to see the general structures. You have the oxetane structure here, and then combined with either a aromatic systems here. You have an interesting one where we now combine it with methacrylate system, and here's a dioxetane. So you're able to modify your properties of your final cured systems using one of the oxetane systems. Some of the advantages for oxetanes when compared to epoxides, this is from the UVEB technical brochure, they tend to have lower skin and eye irritation, cause lower skin sensitization, lower potential for mutagenesis, tend to be lower in toxicity, and little or no odor. So they're very, very good materials to use in your formulation, not only from the properties, but also from a safety and handling perspective. You can also have the epoxy monomers, and here we have vinyl cyclohexene monoxide, limonene dioxide, which is used commonly, and there should be bonds here, vertical bonds, which are gone here, and limonene monoxide. These can be used in a manner similar to monomers are used in free radical systems, primarily to dilute your systems and lower the viscosity. You can also use vinyl ethers in your formulation. Here's a range of different ones that have been used in the past, both monofunctional vinyl ethers and difunctional vinyl ethers. These were very popular and very common, I'm going to guess, say 10, 15 years ago in UV curable cationic chemistry. They're used less so now, primarily due to lack of availability. Some of the suppliers have moved on to other materials and are no longer trading in making these materials, so it's a little bit harder to get a hold of. But there's some advantages of using vinyl ether that are out there. Let's compare it to epoxy structures. Okay, in an epoxy structure, you get minimum shrinkage on that because you're ring opening. However, for vinyl ethers, they act more like free radical acrylate, methacrylate systems, and you can get up to 10 to 20% shrinkage. Both epoxy and vinyl ethers post-cure, so you're able to take advantage of that. Where vinyl ethers really shine, and when they have an advantage, is in their reactivity. So epoxy is relatively slow cure. Vinyl ethers cure very, very fast, so they help speed up your reaction. So if you need to to get your UV curable cationic formulation cured at a little bit higher line speed, you may want to add some vinyl ether. Again, a downside with vinyl ethers, because they're not available in as large quantities as the epoxy materials, they tend to have a higher cost. So in your formulation, you need to balance the pros and cons to decide, is it worth using. Here's comparing the rates. I mentioned how fast vinyl ethers are in the previous slide. So let's compare them. Usually the good benchmark is acrylates. They're very fast reacting in free radical systems. Vinyl ethers are actually react very close to the speed of acrylates. So that's where you get your boost in reaction speed. Next down is cycloaliphatic epoxides, followed by methacrylates, and regular aliphatic epoxides tend to be the slowest in system. This is work done by Charlie Hoyle years ago, and it's a great way to illustrate the relative reactivity of common systems that we use for UV curing. Another component of UV curable cationic systems are the additives. Mentioned earlier that pigments, so your coloring, you'll definitely, of course, using these in inks, but it could be in coatings. You may use fillers, defoamers, flattening agents. One of the properties of cycloaliphatic epoxides, especially CAE, is they give a great looking gloss coating. But if you don't want a gloss coating, you would probably want to add either some silicas or waxes or microspheres into your formulation. You may need wetting agents to wet out on your substrate or slip aids. One thing to note, and definitely remember, avoid using basic or highly acidic materials as additives. And when you think about it, it makes sense. Basic materials would tend to quench your acid that's generated to start your reaction. So you're pretty much dead before your polymerization starts. And highly acidic materials may actually kick off your photopolymerization before you wanted to. So you avoid basic and highly acidic materials, and you'd be fine. You can add hydroxy-containing compounds to your systems, and these are alcohols, polyester polyols, castor oil, maybe CAB, cellulose resins, phenoxy resins, and so forth. These will frequently improve the cure speed, flexibilize your cured coating or ink. Definitely, and not the least important, lower the cost of your systems. You may modify viscosity, use it to modify viscosity, and for some cross-linking. So it becomes very useful material used at relatively smaller amounts. Be very helpful. So now as we went down on our formulation list, we're coming to one of the key components here, and that's the photoinitiators. So these are the materials that when exposed to the UV energy will kick off the reaction. By far and away, the most common photoinitiators used in cationic cure chemistry is sulfonium salts. These are available in two different forms or two different types. One is the triaryl sulfonium hexafluorophosphonate system. Let me get the pointer here. Or the counterion of the hexafluoroantimonate system. So we have the hexafluorophosphonate and hexafluoroantimonate system. When you purchase these or obtain these from a commercial supplier, they're typically supplied as a mixture of these two components. And here's the antimonate system. It works, I think, the same for the phosphonate. You have the sort of mono and the di system. That doesn't affect your activity or doesn't affect the ability to use these materials. They work perfectly well as a mixture. So you'll find them as mixture. They're available as a solid, as you could expect when you look at the structure here, at that molecular weight and overall structure. They're going to be more of a powder. However, it's easier to use liquids. So I believe most of the suppliers of the initiators Also make them available in a solvent, and propylene carbonate, as we have a structure here, is most commonly used. So that it doesn't affect the overall reaction. So you usually see these as a liquid and as a mixture of components. Another class of cationic photo initiators that are commonly used is idonium salts. And we have the structure here. Instead of sulfur, we have now idonium. These tend to be less reactive than sulfonium salts in lab tests. They're also less thermally stable than sulfonium salts. However, they give excellent depth cure when used with either anthracene or thioxanthone systems. So they're a good tool to have in your tool chest when you're formulating. Again, not as commonly used as sulfonium, but they're still used quite a bit out there, and they're very useful. I mentioned with the idonium that you can use them with thioxanthones or other type of sensitizers. One that's probably most commonly used is the anthracene derivatives, and I have the structure here listed. These absorb longer wavelengths of light and then transfer that energy to the photoinitiator. So a small amount of these materials, the anthracene derivatives in your system, will accelerate your cure speed, and it also enables curing of thick coatings. Let's see if we have, and here's the mechanism. So this is from work done by Crivello back in 2003. So you have your synthesizer, UVS, system exposed to UV light. It then reacts with a typical photoinitiator here, and it's the idonium salt, transfers the energy, and then allows that photoinitiator to do its thing and form the cationic system needed to kick off a photopolymerization. Here's some work that was done on comparing idonium salts and sulfonium salts, and to illustrate how well they can accelerate your cure speed in a cationic cured coating. In this case, we have there it goes, an idonium salt and a sulfonium salt, so blue is idonium, the red is sulfonium. So at a straight base formulation, you get, this is a thumb twist cure, so basically it'll putting your thumb on your cured coating and seeing if you make an impression here. So perhaps 15, in this case 15 minutes for the sulfonium under lab conditions, 30 minutes in this case under this experimental condition for idonium. By adding a little bit, and now we're talking parts, or percent, I mean, 0.5%, we drop for idonium from 30 to 15 to cut it in about half, a little bit less for the sulfonium. Going up to 1% of anthracene derivative into your formulation, you've now dramatically reduced your cure speed. So, and this is using a UV LED lamp at 395 nanometers. It could work in the thick film by the fact that the long wavelengths of light are what reaches usually the bottom of thick coating, and most of the photoinitiators are not sensitive to that longer wavelengths of light. However, anthracene derivatives are sensitive, so it will absorb the light at the bottom, near the substrate of a thick coating, transfer that energy to photoinitiator, and now you kick off that photopolymerization, and now you're able to cure a thick coating. So that's how it works with the thick curing. So these are really nice tools to have in your formulating toolbox for both cure speed and thick coatings. Now I talked about the two major types, the sulfonium salts and idonium. You can use other types of cationic photoinitiators. However, these are used in more academic situations and not as much commercially. You can use diazonium salts, ferrocenium salts, and so forth. But really the market is dominated by sulfonium and idonium salts when it comes to cationic photoinitiators. So let's talk about formulating strategies. So we illustrated the mechanism. I talked about the individual components that are used to formulate it, but how do you get it to perform the way you want it to do, to get that final properties you need in your coating or your ink or your adhesive? Here's what I'd like to cover over the next few minutes in our discussion. What you can do to increase your activity of your UV curable cationic system. How do you modify viscosity? How do you modify flexibility? How do you cure thick films? Kind of just touched about that a few minutes ago, but we'll go over it again. This way you'll have it as a good cheat sheet for further, for when you do your own formulations. How do you increase hardness in improving adhesion? So these are different tricks or findings that I've seen over the years, and I've compiled them up in basically one section here for you. Okay, let's start out with formulating for reactivity. One thing you do if you need to have your reaction cure at a greater speed, you can modify the cycloaliphatic epoxides. Ester-free cycloaliphatic epoxides tend to react faster. When you add the polyols, the optimum epoxy to hydroxy ratio is around 3, so you tend to get the greatest cure speed at that level. You can add a UV sensitizer, such as 9,10-dibutoxyanthracene. So one of the anthracene derivatives. Increase cure speed, and we saw that illustrated very well in the chart a few slides ago. You can use a low equivalent weight polyol, like ethanol, monohydroxy, isopropanol, tripropylene glycol, etc. Increase photoinitiator quantity, similar to what's used in free radical systems. So if you're say, I'll pick a number, at 1% photoinitiator, you may want to try 1.5 or 2. Like most systems, you'll reach a point where you get diminishing returns by adding more photoinitiator, and you'll start losing reactivity because you'll start getting the photoinitiator basically absorbing the available light that's out there. You can warm the formulation or preheat the process with either IR radiation or hot air. Remember back when we talked about the mechanism of a UV curable cationic system, I mentioned that after the UV energy kicks it off, then becomes more of a thermal process. So that's why here, by adding heat to your system, warming it, you'll be able to accelerate that curing process. Also work in a dry atmosphere, so dry air will tend to sometimes speed that up. If you want to formulate for a viscosity decrease, say you want to lower your viscosity because of your coating system, there are multiple ways you can do that. You can add the vinyl ether. These tend to be very low viscosity systems, and I have a few listed up there that have been used in the past. Now these vinyl ethers are excellent in reducing viscosity, so they're great diluents. However, they do tend to negatively impact your solvent resistance of your formulation, so you have to kind of balance that property out, depending on what you want to achieve. Epoxy diluents can be used, so like an aliphatic epoxide, limonene dioxide is commonly used, or ETHB is another one. But something to remember if you're using epoxies to dilute it is that they're less efficient in reducing your viscosity. However, a real upside to using them is that they have high solvent resistance and add some flexibility to your system. You can also add alcohols, and as alcohols, like a typical organic solvent, will really cut that viscosity down. So you wouldn't use a lot, depending on your system. The amount could be just a few percent, up to the 5–10% range. You use low molecular weight glycols, such as tripropylene glycol or diethylene glycol. Alcohols are also really excellent in reducing viscosity, and not to mention lowering cost. They negatively impact solvent resistance. So if you're in an application that requires this, you would probably want to avoid alcohols as diluents if you do need to use diluents. And strangely enough, water can also be, can on occasion be used to dilute your UV curable cationic system. And I know I just mentioned earlier that water will you would, if you're using a UV curable system to increase reactivity, you may want to use this in a dry system. However, water can be at times stabilize your UV curable formulation, and I've seen commercial applications in the past that actually intentionally added, say, 2% or 3% of water to make sure that their UV curing system, basically their line speed is consistent day in, day out, season in, season out. So you can use a little bit of water. I would be very cautious, though, on using much more than a few percent. So I've seen it listed as up to 10% working well. Okay, what if you wanted to go in the opposite direction? Instead of reducing viscosity, you needed a higher viscosity in your formulation. For example, if you're applying it to a vertical surface or a surface that's on an angle, and you don't want it to start to creep before it fully cures. In this case, you could blend in a cellulose acetate butyrate or CAB material to increase your viscosity, perhaps use an epoxy Novolac resin or epoxidized polybutadiene, or perhaps a high viscosity polyol. So all these are good ways of adding to your formulation to increase the viscosity, yet still get a good curing material. For flexibility, there are various methods you can use. You can add a triol add an epoxy to hydroxy ratio of 3:1 to 6:1, such as caprolactone triols or propoxylated trimethyl propane. You can use a modified cycloalpha epoxides. Which are, think of it, and let's see if there's our arrow here. Because these long aliphatic chains here, and then what's going to be here, will give you that flexibility once they cure in your system. Or just straight, this should be an aliphatic epoxide. Straight aliphatic epoxides work well. Or you can use epoxidized polybutadienes, epoxidized oils like soybean oil or castor oil, or polycaprolactone are used for flexibility. So there's numerous ways you could formulate to make some system more flexible than, say, your baseline formulation. We talked a little bit earlier about formulating for in-depth cure for very thick films. Again, anthracene type materials are very efficient in thick films at concentrations up to 0.3%. So you don't need to add a lot for them to be effective. ITX can also be used. Here, ITX tends to be effective at concentrations at lower than 0.1%. When you have a cured, like say, a thick film that you're trying to cure, you can also help the surface cure by perhaps using a hybrid system, an acrylate blend. We'll be talking more in depth on hybrid systems following this section. If you're going to formulate for hardness, you can increase the cross-linking. So you use some commercial cycloaliphatic epoxide polyol blends that are available from different suppliers. You can increase the T sub G of your photopolymer. Again, going to a commercial cycloaliphatic epoxide polyol blend that is formulated specifically for increasing hardness or increasing T sub G. You can mix in reactive resins such as epoxy Novolac resins or high functional glycidyl ethers, and of course your post-bake to further push that reaction, push that photopolymerization, and make a more reactive photopolymer. Here's an example of that I found in the literature on increasing the tensile strength by adding a polyol here, or this system. So this is from a Placel series, a generic Placel series. So we have these polyols here, and one particular was designated PCL303. Using our base, our workhorse cycloaliphatic epoxide, CAE, you get a tensile strength of very roughly around 27 millipascals. Adding 5% of PCl3, so adding 5% of this material, 10%, 20%, and so forth. We see we increased the tensile strength of your cured photopolymer from a 27 to something in the low 70s. So a dramatic increase of tensile strength simply by formulating in this polyol. Say if you wanted to formulate for adhesion, it could be because it's a difficult or challenging substrate, or you're actually formulating for a cationic adhesive. You can use a modified cycloaliphatic epoxide. Here, you can use an aliphatic resin such as hexane diglycidyl ether. It tends to improve your adhesion of your formulation. Vinyl ethers have a real strong ability to reduce the viscosity, as we talked about earlier, but they also maintain the adhesion at the same time. So you may want to add a few percent, 5 to 8% of a vinyl ether. Another very simple way is just changing your photoinitiator. It's something that when you formulate, we may not think of at first, but perhaps by using the phosphonium, the hexafluorophosphonate sulfonium salt, as photoinitiator instead of the antimonate salt, you get usually a bump in adhesion, primarily through the presence of the phosphorus in your formulation. So that's a real simple way of proving your adhesion. Should you want to, you need to improve it. Okay, we talked about all the ways you can improve and modify cationic systems. Many of us are familiar with radical systems. How do they compare? How do radical systems compare to cationic systems? On this slide, I have a comparison head-to-head of radical versus cationic. For radical, you get a wide variety of raw materials. There's probably thousands of commercial acrylates and methacrylates you can get to formulate. Cationic, you're more limited in raw materials. You have some very good ones. You have your workhorse materials. You have your vinyl ethers and oxetanes, but still compared to acrylates, methacrylates, it's much less in number. Radical chemistry, UV curing, is inhibited by oxygen. Some applications it doesn't matter. However, in others, it's a real challenge to work around or an expensive problem to have. You may have to have a nitrogen blanket. You also have in radical chemistry, it's not inhibited by high humidity. Cationic, because of the mechanism, there is no oxygen inhibition. So you can just run right in the open air and it will cure very well. However, you then get potentially inhibited by high humidity at times. Now, it may not fully kill it off, as we've talked about adding water, but it will still vary your rate of reaction. So you'll see a change in cure speed. Radical chemistry is not inhibited by basic materials. In fact, there are amines, for example, or acrylated amines that are used in radical cure. Cationic, you can't use basic materials. It will just kill the reaction completely with your acid catalyst, the acid photoinitiator. Radical chemistry cures, you get full cure in seconds, where cationic may take hours. You'll get your initial properties locked in, but to get the final properties may take hours. And in many cases, that really doesn't matter. Radical curing, you get quite a bit of shrinkage. You can get 10 up to 20% shrinkage, which causes problems, especially adhesion. Cationic, one of the great advantages of UV curable cationic chemistry is that the adhesion is much better. Maybe because for the most part you're using ring opening. You're not losing reaction volume during the photopolymerization, so you don't get the shrinkage. Depth of cure is greater in free radical chemistry, much less in cationic cure. But with the use of anthracene derivatives, you get around that very, very easily. And overall, radical chemistry probably has in the low 90s market share versus 6, 8, 9% or so for cationic cure. So you have that relative balance there. Now for the remainder, or not for the remainder, for the next section, I want to touch upon hybrid systems because this is getting really creative. It's kind of taking the best of both worlds here, free radical and cationic. So hybrid systems, when I refer to hybrid systems in the webinar context of today's webinar, I'm thinking of the use of free radical and cationic polymerizations and UV curing in order to improve the properties. So having it that combination is something better than singular. And I think a good place to start out with, when we're talking about hybrid cure, is that of IPNs, or interpenetrating polymer networks. What an IPN is, it's two or more polymer networks that are permanently tangled, but not covalently linked to each other. So think of them as two different threads in a ball of yarn that are just mixed up in there. So they're not connected, but they're just fully tangled. Two different processes can generally occur when you're forming that tanglement. You can get a polymerization of the two components simultaneously, so you have both reacting and independently, and as they're growing your polymer chain, they just grow around each other, and you get your tangled ball or polymer. Or you can initially have one polymer being formed, so it reacts first, so you get your polymer. It's then swollen by the liquid monomer of your other component, and then that polymerizes. So you can think of it as both happening at the same time, or first one and then the other. Now when you mix acrylates and epoxide systems, they tend to produce IPN. So that tends to be the usual outcome when you blend a free radical system and a cationic system. Why would we want to do that? Well, IPNs can produce some cure properties that are very unique when compared to an individual acrylate or an epoxy system. The final properties are determined by the monomer that you're using and their polymer miscibility, their compatibility, the polymerization method, your order of polymerization, what reacts first, what reacts second, the cross-linking density, and the reaction kinetics. It seems like a lot there in that bullet, but when you think about it, that just means you have a lot of dials that you can change to perhaps tweak your properties of your finished cure system. So I look at that as a real advantage as opposed to just a lot of things you need to just keep in track of. The remaining epoxy cationic chemistry will continue to dark cure. So after you form your IPN, the epoxy cationic chemistry will continue its thermal route, and that will result in a change of properties for some time after exposure to UV light. So you will have this shifting of properties. Many times, or even most of the time, that's actually preferred. That's a good thing to get to your final properties. So dark cure does not go away. You can get potentially higher acrylate conversion in hybrid systems when compared to 100% acrylate systems. 100% acrylate systems, as they cure, you'll get a very fast formation to the gel or glass state, and that may tend to isolate acrylate bonds. So you may only get curing in a solid, what you think is a cured free radical system, of maybe 70, 80%. With hybrid systems, you get a much more complete acrylate cure. And this is due to that delay in forming a rigid glass-like state. Oxygen inhibition of the free radical system's component is frequently reduced. And this is likely due to the viscosity increase as the epoxide component is polymerized. So you delay that glass state, and you tend to get a little bit further reaction, and you get reduced oxygen inhibition. One thing to remember is that urethane acrylates will inhibit the cationic polymerization in hybrid systems because of the urethane functionality there. So they will react with your acid generated system and slow down or potentially kill your reaction. So you just have to steer away from urethane acrylates. In addition to acrylate epoxy hybrid systems, other combination of materials can be used, such as thiolene or thiol epoxy resins with your epoxy system to get hybrid polymers. Here's a great illustration of how that combination works. So the combination is better than the individual components. This is work done by Christian Decker, and back in 2001, where he looked at an acolyte system, and he got in the y-axis is the hardness, and there's exposure time in seconds. So you formed a certain hardness here after stable. It takes 3 seconds. The epoxide, cycloaliphatic epoxide system, cationic system cured, you got a great increase in hardness. However, the best hardness obtained was actually the hybrid system. Instead of coming out what seems to happen most often, you get something that's a compromise. It actually combined, and you got a much harder cured photopolymer than you did with individual components. So this kind of, I thought, very nicely illustrates how hybrid systems can work to your advantage. There's another type of hybrid systems as an alternative to IPNs that can occur that are also very interesting, and this is photopolymerization induced phase separation. This is, on the next couple of slides, I'm going to report on work that Ariane Haza of the University of Iowa has published in this area. And instead of forming your IPN, your tangled web, or a ball of yarn, you get actually phase separation, and this develops as the different or orthogonal chemistries between radical and cationic monomers as they react, they induce thermodynamic incompatibility. So they basically kind of push away from each other and form domains. So photopolymerization rates play a significant role in determining domain size and continuity. An indication of phase separation is the presence of different glass transition temperatures of the final photopolymer. Here's a great illustration that Ariane Haza has published to show this. It's the balance between the gelation and phase separation, which determines the final polymer nano or microstructure, and the light intensity can be used to control the rates of reaction and determine your final properties. In this case, Ariane took this acrylate for hybrid system composed of BA, butyl acrylate, and this oxetane. And if you just take the oxetane itself, and he exposed the system to 10 milliwatts per square centimeter of light, 100 milliwatts, and 1500 milliwatts. So, and the properties of the oxetane or DOX in toughness can be found here. So somewhere between 0.2, 0.4. However, when he combine that in a hybrid system, so we have DOX to a BA ratio, so 7:3, and compose it to different levels of light, here we see a dramatic increase in the toughness of the system. So using, and just as you see the low level light, at the lowest level, barely any reaction there. Something comparable at the 100 milliwatts. However, at 1500, you got a dramatic increase in toughness. So just by using the light intensity, you're able to modify properties. And finally, before we leave hybrid systems and our webinar, I'd like to talk about combining both functionalities in one molecule. So these are compounds that contain both cationic pure and a free radical reactive group in the same molecule. So we have here's our cycloaliphatic epoxide joined at the hip to a methacrylate. These are commercially available, by the way, so they do exist and are readily available. These react in a similar manner to methacrylates in free radical cure. They also react in similar manner to cycloaliphatic epoxides, the cationic cure. So this now allows the preparation of a coating, ink, or a 3D printed object that contains either an unreacted epoxide or methacrylate groups. And then these groups are now available for further reaction if you want to functionalize your photopolymer. So you can be very clever and do some things other than just a straight UV cationic photopolymerization or free radical photopolymerization. Now, if you noticed early on when I introduced hybrid systems, I had some photos up on that slide, and one showed a few a selection of 3D printers on a lab bench. Another one was a 3D printed object. And there's a reason for that, is that hybrid systems are becoming very popular ways of approaching formulations for UV curable 3D systems or additive manufacturing. It's because the fast cure of the acrylate components followed by the slower development of cationic materials during dark cure is a very useful combination to have when 3D printing. The desired result is that you get the formation of your printed object very quickly, known as the green state. You could then take it out so the acrylate's formed. You take it out of your bath. You can handle it without breaking, without deforming it. And then you let the final physical properties form during post-cure. So this allows targeted mechanical properties that would be really difficult to achieve from either a pure acrylate or epoxide systems. I like to wrap up, and I'm not going to go over these in any detail, but the last few slides, I wanted to show some examples of cationic formulations. So, there it goes. So I have starting point formulations, and these are old. I picked these in literature. They've been around. They're probably not state-of-the-art, but of a laminating adhesive, metal coating, clear coat, flexo, printing ink, and a printed circuit board. And I'll just go over, say, one here. And this is for a laminating adhesive. We can see where the CAE is a major component, but in general, formulations are not that complicated for UV curable cationic systems. Once you start doing them, they're very similar to working with free radical on that. So you get very simple systems, and I have overprint varnish here, and we're going to kind of zip to the end here as we're about out of time. Flexo ink, and you can look at these, and you'll have these as a reference. And finally, I like to acknowledge the very strong support and the great help of Nagase America Corporation, with help also from Diacell, Chemtech, Tal Gosai, UVEB, and Arian Haza at the University of Iowa to help put together this some of the information that I use for this webinar. So hopefully in the last hour you've got a good understanding of some of the basics of UV curable cationic curing, also how it can be used, how you can modify it. In my opinion, that the UV curable cationic cure is a really good tool to have in your formulating tool chest. It won't replace free radical cure, but there are some opportunities where it is the perfect fit and it is the best fit for solving a photopolymerization coating, ink, adhesive, and so forth. So with that, I'd like to thank you for your attendance, and I think we may have time for a few questions here.
Thank you very much, Mike, and sorry for losing the bonds there. So I know we're at 3 o'clock, but maybe if there's just a couple of questions for Mike, otherwise you can always follow up with them afterwards, or if you go to the UVEB conference in March, I'm sure he'd be happy to answer all of your questions there too.
Yes, and I promise I won't talk your ear off if you catch me at the UVEB conference. And by the way, in addition to contacting myself for just general information about the content of this webinar, for more detailed information on the materials and 3D applications, contact Jeremy Smith, and his contact info is on the slide there, or for coatings and ink applications, Tony Franklin. Okay, we're having some questions come up here. One question is what is the silane additive used for? One of the areas that silanes are used quite extensively in UV curable cationic cure is for release coatings. These are the coatings that are put down so that when you have a label, an adhesive label, or stick to it, that's that smooth, very low stick surface that's coated first before they add the label to it. So it's for quick release coatings. Another question is, how about the shelf stabilization of formulated systems? They're quite good. They're essentially no difference in my experience than free radical systems. I've seen UV curable cationic systems stable on the bench. So these are as liquids for over a year and a half. I think the studies maybe perhaps longer, but they're the ones that I've seen from a practical end. Like any UV curable system, after about a year, you'd want to test viscosity to make sure you're not getting any drift, that there isn't a contaminant in there. But you can get rather long shelf life with UV curable cationic systems. So what are problems that you get due to Lewis acids in your cured system? That's a great question. These are at low enough level, and I think they end up getting trapped in the polymer. I've seen essentially no problems with the Lewis acids remaining in a cured system for coatings that have been used in quite a variety of applications and for extended period of time. So I haven't seen any degradation, but I really like that question, and I think you're going to spark me to do a little bit of research to see if I can find if anybody has done any experimental work to look at that. But from a practical point of view, there's essentially no problem having the presence of that acid in your system. Got quite a few questions coming in here. Let's see. Do photocatalysts without sensitizers absorb in 395 nanometer range? I'd have to take a look at that. I'm not sure. I don't have the absorption spectrum, and I work a lot in free radicals, so I don't want to speak off the top of my head, and I just can't quite remember now where the range of those photoinitiators absorb in. So I can get that question out to you. Just drop me an email, and I could find that for you. Here's an interesting question. Can cationic UV curable systems be applied to 100% solid materials such as powder coatings? I can't see why not. It would be very similar to UV curable free radical powder systems. You would have to have a cationic system that would be solid and that would melt low enough so they would flow, and then then you could hit it with the UV energy to cure. Off the top of my head, I can't think of any that have been used, but there's nothing inherently that would serve as a roadblock to that process. Another question is can these systems work only for films? And the answer is no. In fact, there are, like in the hybrid systems, so we'll take that, are now used for some very high performing 3D printed systems. So it's a bit more thick, quite a bit thicker type systems, applications. So use from them. They're used for adhesives also. So they can be used for more than films. They're not limited to films only. Hybrid systems use both initiators. Yes. I guess if I understand this question correctly, do hybrid systems use both a free radical initiator and a cationic cure system? And yes, you would need some way of generating both free radical and an acid system for your formulation. Okay, an example of a composite application. They were used, the composite applications, and in fact, I'm going to bring back, just because it's a little bit different, but I'll give you a good example. I had mentioned early in my webinar that I was involved in an electron beam curing cationic system, and this was to make composites. So these were for making exterior high-performance aircraft parts. They were also used for making Formula One components for exterior Formula One race cars. So very thick systems. They would lay fiberglass in the cationic cure system, and then hit it with the electron beam energy to cure their system. So that would be one example of it. If you're using just straight UV light, UV energy, you would need an anthracene derivative in there as you get into thick composites to make sure you get fully cure. However, once you kick it off from the surface, and by continuing the dark cure, you probably get rather extensive curing below where that energy has traveled. Okay, another question here while we're in the hybrid systems. Is it necessary to modify the spray parameters? No, it isn't. You would basically want to set your formulation to get the correct viscosity that you require for spraying. But other than that, they tend to work very much like single component systems. And when I say single component, I mean free radical or cationic type systems. Thinking about it, I don't recall much, if any difference in using hybrid systems when spraying.
I think we're going to need to wrap things up. Thank you, Mike, for sticking around to answer questions. Is it all right if you didn't get to the questions that people can just follow up with you via email?
Yes, definitely. I would. Please feel free. We will, and I'll do my best to get your answers to it. And we'll have to take a look. But I think when we post the presentation online, we'll correct all the missing structures that were on this version, and so you'll be able to get a presentation that looks a little bit better. Thanks for your patience in that.
Yeah, sorry about that. Some of the lines just got clipped in the conversion. But thank you, everybody, for tuning in today. Thank you very much to you, Mike, for putting this together and for your time in this. Keep an eye out for an email. I'll give you the link, and we'll have the recording for this up in the next day or two, along with a PDF of the slides with the correct structures on it. And keep an eye out for an email from Mickey about our next upcoming webinars. Thank you, everybody, and have a great afternoon.